Alright class, we've been talking about buffers. We talked about what buffers are, a weak acid and its conjugate, a weak base and its conjugate. We did a couple practice problems with buffer last time, and we're going to continue keep doing these practice problems with buffer. Now, here's a question. Take a minute, you can pause me, you can read this question. Now, if you look at this question, I'm adding hydrochloric acid to a buffer solution. And if I hadn't told you that this is a buffer solution, I know I told you it's a buffer solution, but even if I hadn't told you, you would have known it's a buffer solution because you have ammonia and ammonium chloride. So you have a weak base and you have its conjugate. Okay. And it asks you how much the pH will change. Well, first we have to calculate the pH of the original buffer solution before adding the acid. Okay. So let's do that. So before we add any acid, let's figure out what is the original pH of the buffer solution before we add the acid. So we have ammonia, which is a weak base, right? You have a weak acid or base. What do? You already know the answer to that. Every time you have a weak acid or base, you're going to write the equilibrium, right? So here's my weak base, ammonia. Base are going to get a hydrogen. That means water is an acid. Acid is going to lose a hydrogen. Base gets a hydrogen. The acid loses a hydrogen. So what's going to happen is my base is going to get a hydrogen. It's going to become NH4+. So water is going to act like an acid then, and is going to lose a hydrogen. Is going to become OH-. Okay. Now, is this a buffer problem? This is a buffer problem because, why is it a buffer problem? So I have 0.100 molar of ammonia. Now, if I only had the ammonia, this would not be a buffer problem because the percent hydrolysis to form ammonium is not much. But this is a common ion problem. I also have some ammonium chloride in the solution. And remember, if I have ammonium chloride in water, it has 100% dissociation. I have ammonium and I have Cl, right? So what that means is, if I have, how much do I have? If I have 0.200 molar ammonium chloride, 100% dissociation, it breaks up, and what would I have? I would have 0.200 molar ammonium and 0.200 molar Cl-. Cl- is not going to do me any good, spectator, but ammonium is my common ion effect. Ammonium is my common ion effect. So what that means is I also have some ammonium in the solution. Okay, so in this solution, what do I got? In this solution, I have a weak base and I have his conjugate base. Conjugate acid. So I have a weak base and I have his conjugate. If I have a weak base and I have his conjugate, what do I have? That means you have a buffer problem. That means you have a buffer problem. And we've talked about this before. If you have a buffer problem, yeah, you could do the ice table and figure out the X, but there is a faster way. Every time you have a buffer problem, you can also use the HH equation. And HH equation is so much faster than this, than doing the ice table. So what was the HH equation? Remember, the HH equation was POH for bases would be PKB plus log of ammonia on the weak base bottom and the conjugate acid on top. Again, you can also do the whole ice table, but this is so much easier when you have a buffer solution. Now, the KB is given to you. If KB is given to you, can you figure out the PKB? Yes, you can, because minus log of KB gives you PKB. Okay, so in this problem, minus log of 1.8 times 10 to the minus 5, if I do that, what I end up getting is 4.74, which is going to be my PKB. Okay, that's my PKB. Now, I'm going to come over here and I'm going to plug it in. My PKB is what? Is 4.74 0.74 plus log. What is my ammonia concentration? Hopefully you're yelling. That is 0.110. What is my ammonium concentration? 0.200. Okay. Now, if I do this, if I plug everything in, what I end up getting for pOH is 5.046. Again, you know how to do this. Once you have pOH, it's easy to figure out the pH. All you have to do 14 minus 5.046 is going to give me 8.95, and that is my pH. That is my pH. Okay. So here's the pH of my buffer solution before I add anything to it. Okay. Now, before we do part B of this, let's think about this conceptually. So here I have a buffer solution. I know it's a buffer solution because I have a weak base and I have this conjugate. So I can figure out the pH using HH equation. This is the pH of my buffer solution. Now, let's think about this conceptually first. I have a buffer solution. The pH is 8.95. Now, what I'm adding to it, I'm adding a strong acid. If I add a strong acid, do you expect the pH to change much? No. You are adding a strong acid, but because this is a buffer solution, and the buffer solution has a tendency to resist the pH change, we don't expect the pH to change much. Well, let's figure out if the pH changes much or no. So now the second part is we add acid to this solution. We have acid to this solution. Okay, so I have a buffer solution and now an acid is added. Now we need to think about this. So I have a buffer solution and what's added is an acid is added. Now, what type of problem do I have now? Every time you have a buffer solution, now an acid is added. Now, what type of problem do I have? Now, what you have an acid-base reaction. Now you have an acid-base reaction. Now, check this out. If you add acid to this buffer solution, the acid will not be attracted to ammonium because ammonium is also an acid. It's not going to have any reaction. Acid on acid does nothing. But the acid, the HCl, is going to be attracted to the base. Acid-base reaction are the fastest reaction in chemistry. Remember that. So I have an acid-base reaction. This is my acid. Acid on acid does nothing. But HCl is going to be attracted to the base, which is ammonia. Okay? So it's going to be attracted to ammonia. And I'm going to have an acid-base reaction. Now, every time you have an acid-base reaction, I need you to remember a few things. Acid-base reaction are not equilibrium reaction. They are not equilibrium reaction anymore, which means you're going to have a single arrow. Every time you have acid-base reaction, you have to use moles. And every time you have an acid-base reaction, you have a limiting reagent problem. You guys got this down? Acid-base, not an equilibrium, single arrow, use moles, and limiting reagent. Okay, so this was our original buffer solution. We figured out the pH of this. I added acid to it. Acid not attracted to the conjugate acid. Acid is going to be attracted to the base, acid-base reaction. So let's write down this acid-base reaction, which means HCl is going to be attracted to ammonia. Single arrow, the acid is going to lose a hydrogen and the base is going to get a hydrogen. So I end up with NH4, basically NH4Cl, because it's going to lose the hydrogen and this one is going to get the hydrogen. Okay, now here's my acid-base reaction. The acid is going to go react with the base. Now I'm not going to have an ice table because it's not equilibrium. I'm going to have an ICF table. F is for final instead of ICE, which is E for equilibrium. Now I said not an equilibrium, we did a single arrow. Now in this problem I made it easy for you because I said it is in 1 liter. Because it's in 1 liter, then my molarity and moles are the same. So how many moles of the HCl do I have? I have 0.020 moles of HCl, and I have 0.100 moles of ammonia, and for ammonium I have 0.200 from the last problem, right? So I have this problem, this one, and this one. I already have it in the solution, and that goes there. Now the same thing as before. This is minus x minus x, and this is my x. Now we use the moles. Now limiting reagent. I have 0.020 moles of hydrochloric acid react with 0.100 ammonia. Which one is my limiting reagent? Hydrochloric acid is my limiting reagent. So HCl is my limiting reagent. Okay. So again, this is a mole ratio now. This is a limiting reagent. Don't confuse it with the equilibrium. It's not an equilibrium, even though we have an X. So what is going to be my X? My X is going to be 0.020 because my X is the limiting reagent. And again, remember, these are all moles, but because we had 1 liter solution, molarity was the same thing as moles. So that's my limiting reagent, which means I'm going to use 0.020 minus 0.020 plus 0.020. I'm going to have none of the HCl left. Every single HCl is going to react with ammonia. But I'm going to have 0.080 moles of ammonia left and 0.220 of ammonium chloride left. So far so good. Okay, so this was an acid-base reaction. Now what type of problem do I have? I have ammonia and I have ammonium left. I'm hoping you're yelling the answer right now. I have a buffer problem now, don't I? Because after I did the acid-base reaction, check this out. Now I have a weak base and I have its conjugate. So now I have a buffer problem. Now every time you have a buffer problem, remember, what can you use? You can use the HH equation. Let's do it. Let's use the HH equation. So POH, because I have a base, equals PKB plus log. Down here is ammonia, up there is ammonium. PKB again from the last part is the same. PKB is going to be 4.74 plus log. Now my ammonia is 0.080. Again, is 1 liter, so moles and molarity are the same. And ammonia is 0.220. Okay. When I do everything, POH ends up being 5.18. Now, 14 minus 5.18 is going to be 8.82 is going to be my pH. Now, before we added a strong acid, the pH was 8.95. We added a strong acid, the pH is 8.82. Did it change much? It did not change much. It did not change much. Okay? So it did not change much. Nice job. Now, let's do another practice problem. Here is our next practice problem. Okay, so here is our next problem. You can pause this and then read this question. So what do you have here? What you have here, they ask you to calculate the concentration of H plus and the pH. Solution you prepare by mixing acetic acid and sodium hydroxide. Solution of acetic acid and you adding sodium hydroxide. Okay, so this will be your take-home problem. Okay, and we're gonna come back to this in the next video, because I'm going to talk about one more thing before I go over this. But this is your take-home problem. Do the best you can with this, and then we'll definitely go over it next time.